Let's take a look now at some trigonometric integrals. And what we're going to work with first is integrals that involve powers of sine multiplied by powers of cosine. And the basic idea is to use the power rule. Now, these identities are going to come in really handy. Now remember, this identity gives us that cosine squared of x is actually equal to 1 minus sine squared of x, which also tells us that sine squared of x is equal to 1 minus cosine squared of x. These identities will come in pretty handy. And in addition, we have these two identities where sine squared can be written in terms of cosine as 1 minus cosine 2x over 2, and cosine squared is 1 plus cosine of 2x over 2. So these couple of identities will come in extremely useful. Now, the first thing I want to do is concentrate on the idea is what if sine is odd? I have an odd multiple of sine, as in sine cubed, sine to the fifth, and so forth, multiplied by a factor of cosine, or some form of cosine. Now, it doesn't really matter if cosine is to the fourth, to the fifth, to the sixth, whatever. It's the sign being odd that makes this work. And this is actually the form that kind of explains what's going to happen. Because when we write the sine squared in terms of cosine, see, now I'm set up for a U substitution. So what I'm going to do is I'm going to take one sine, pull it out. Remember, sine was odd, so that gives me an even, sine squared, sine to the fourth, sine to the sixth, an even power of sine left, which I can write in terms of cosine. Now, if I let u equal cosine, then du is going to be sine. So it's a nice U substitution. Let's take a look at this example. If I pull out one sine, I can write this as the integral of sine squared of x cosine squared of x times sine of x dx. Now, if I write this sine in terms of cosine, I will have the integral of 1 minus cosine squared of x, there's my sine squared, times cosine squared of x, sine x dx. Now let's do a straight U substitution. If I let u equal cosine of x, then du equals a negative sine x dx. So of course I'm going to write this as a negative du equals sine x dx, which is exactly what I have sitting right there. So I can write this as 1 minus u squared times u squared du. See, I just went from something involving sines and cosines down to a polynomial in u. And of course, I can rewrite this as the integral of u squared minus u to the fourth du, which is u cubed over 3. Oops, forgot my negative sign here. Let's put a negative out there. Minus u to the fifth over 5. This is actually equals right there. So this is going to be a negative of, see, u was cosine, so I'll have cosine cubed of x over 3 minus cosine to the fifth of x over 5, plus I need my constant of integration. Now, you can fiddle around with that and move that negative in or do whatever you're going to do, but essentially, that's the solution. Okay, let's take a look at another example. And this is the exact same idea we just did, only this time we have an odd power of cosine and whatever else of sine. It doesn't really matter. And we're going to do the exact same idea here. And again, this is an explanation of what we're actually doing, so you can take a minute and take a look at that in the generic form. But let's go ahead and jump into this using this example. There's my odd power of cosine. So I'm going to rewrite this as the integral of sine squared of x times cosine to the fourth of x times cosine of x dx. So I have that odd power of cosine. I pulled one of them out. Now I need to write this cosine in terms of sine. So this will be equal to the integral of sine squared of x times 1 minus, oops, missed there, 1 minus sine squared of x. 1 minus sine squared is cosine squared, but I have a cosine to the fourth, so I need to square this, times cosine x dx. Now, if I simply let u equal sine x, then du equals cosine x dx, which is exactly what I need. So I can write this in terms of u. U squared times 1 minus u squared squared du, which let's just do a little algebra. And this is going to be the integral of u squared times 1 minus 2u squared plus u to the fourth du, which equals the integral of u squared minus 2u to the fourth plus u to the sixth du. See, now I have this nice polynomial in u, which I can easily find antiderivatives of. And that is going to give me u cubed over 3 minus 2u to the fourth, to the fifth over 5 plus u to the seventh over 7. But remember, u is sine, so this is actually going to give me a sine cubed of x over 3 minus 2 sine to the fifth of x over 5 plus sine to the seventh of x over 7, and I can't forget that constant of integration. So, absent any other simplification you may want to mess around with, that's the solution to our original integral. All right, let's take a look at another example. Let's now suppose that both sine and cosine are even powers. Before, the whole idea is that I had either sine or cosine as an odd power, and that allowed me to do that U substitution. What if they're both even? Well, if they're even powers, I'm going to use these identities and convert them all to cosines. So, let's go ahead and take a look at this one. I have cosine to the fourth, which is cosine squared squared. So I have the integral of 1 plus cosine 2x over 2. That's cosine squared. I square it, now I have cosine to the fourth. Now if I expand this, I'm going to end up with the integral. I'm going to pull this 1/4 up. See, this 1/2 squared is going to give me a 1/4. See, I'm going to have a 1 plus 2 cosine 2x plus cosine squared of 2x dx. So that's going to equal 1/4 times the integral of 1 plus 2 cosine of 2x plus, I have this cosine squared to deal with, so I'm going to use this identity again. So remember, I have 2 times x. Cosine of x squared is 1 plus cosine 2 times x. So in this case, rather than the x, I have a 2x. So 2 times 2x will be 4x. So this will give me 1 plus cosine of 4x over 2 dx. And I'm going to make 1 or 2 more steps just to help make you see it perhaps a little easier. See, 1 plus 2 cosine of 2x plus a half plus cosine of 4x over 2 dx. See, now I can combine these constant terms. And I'm going to get 1/4 times the integral of 3/2 plus 2 cosine of 2x plus cosine of 4x over 2 dx. Now I'm ready to go take an antiderivative. So this will be 1/4 times 3x over 2 plus, let's see, I know that when I take the antiderivative of cosine of 2x, I'm going to have a sine of 2x. And when I take the derivative of sine of 2x, I'll get cosine of 2x times 2, which is exactly what I want. So that's what I need there. Plus, okay, cosine of 4x over 2. Well, I know I'm going to have sine of 4x. Now, when I take the derivative of sine of 4x, I'll get 4 times cosine of 4x, but I need cosine of 4x over 2, so this must be over 8. Now when I take the derivative, I'll get back this piece that I need. Plus my constant integration c. And I'm not going to mess with distributing this 1/4. I mean, you can fiddle a little bit more if you like to, but essentially, this right here is the solution to my original problem.